This video covers chapter 21, which is comparing two means. We're also going to take a look at t-tests. So what we cover in this chapter is two sample problems, comparing two population means, two sample t-procedures, another look at robustness like we did in chapter 20, details of our t-approximation, avoid the pooled two sample t-procedures, and then how to avoid inference about standard deviations. So first, two sample problems. So when it comes to two sample problems and doing inference about these two samples, the goal is to compare the response to two treatments or compare the characteristics of two populations. So we have a separate sample from each treatment or each population. So we could, when it comes to treatment, be comparing a placebo and the actual medication. When it comes to population, we've got two separate populations. We could be comparing GPAs of college freshmen and college juniors, but we just have two. And a two sample problem can arise from a randomized comparative experiment that randomly divides subjects into two groups and exposes each group to a different treatment. We compare these random samples separately selected from the two populations. That's a two sample problem. Unlike our match paired designs, there's no matching of the individuals in the two samples. We're just matching and looking at the outcome. We assume that these samples are independent, and because it's not like pairs matching, they can be different sizes. And the most common goal of inference is to compare the average or typical response in the two populations. So we're primarily looking at like mean. So the conditions we need to meet for inference about two means is that we do need two simple random samples from two distinct populations where the samples are independent, so one has no influence on the other. That's really crucial. And we're looking at the same response variable for both samples. Like I can't compare the mean and standard deviation. I need to have both means. Both of these populations do need to be normally distributed. That pretty much goes without saying. The means and standard deviations of the populations are unknown. In practice, it is enough that the distributions have similar shapes and that our data has no strong outliers. Strong outliers would not make our data normally distributed. So we can call our first variable x1 in the first population, x2 in the second, because our variable may have different distribution in the two populations. So here's how we describe our two populations. We're going to use subscripts. So for population 1, our variable would be x1. So like if we were looking at height, we would take the mean height for our sample and calculate the standard deviation for this first sample, as well as for our second sample. So for our populations, right? When it comes to our samples, we use our sample notation. So we've got our samples. So from our first population, our sample size would be N1 and our sample mean would be X bar, right? And our sample standard deviation when it comes to the sample is S1. For 2, we'd have N2, X bar 2, and S sub 2, right? So is that from our second population. And what we want to do is compare two population means by giving a confidence interval for their difference or doing a hypothesis testing that there is no difference. So like mu1 minus mu2 equals 0. I could also say mu1 equals mu2. These are equivalent mathematically. To do inference about the difference between the means of two populations, we start with the difference of their samples. And we're going to conduct a two sample t procedure. So to take variation into account, we would like to standardize our observed difference by subtracting the means, right? And dividing the result by the standard deviation. And our standard deviation for two sample means is going to be sigma sub 1 squared plus sigma 2 squared. And we're dividing that by the population size. So whereas before, our standard deviation was just the square root of our standard deviation divided by n. Sorry, not the square root. I made my square root symbol too big. Whereas before we had this, right? Now we are standardizing it by squaring it and dividing by both the sample size. And because we don't know the population standard deviations, we estimate them by using the sample standard deviations of the difference in sample means. So if I have the standard error for x bar 1 minus x bar 2, that's going to be the square root of our sample standard deviation squared divided by this sample size of n1. This is why they don't have to have the same size sample. And then our sample standard deviation squared divided by n2. Okay, so a few more slides and then we're going to work through an example. So what we do then is we standardize the mean and estimate the mean by dividing the difference between the two in this sample t statistic. So t is our sample means, the difference in our sample means minus the difference in our population means over our standard error. So that's like our new standard deviation. And this two-sample t statistic has approximately a t distribution. It does not have exactly a t distribution, even if the populations are both exactly normal, right? In practice, however, the approximation is still very accurate, and there are two practical options for using this two-sample t procedure. So the first being with software, using the statistic t with accurate critical values from approximating a t distribution. And the second is without software, we can use the statistic t with critical values from the t distribution with degrees of freedom equal to the smaller of the sample sizes. And the significance test would give us a p-value equal to or greater than the true value. So to create a confidence interval, right, what we do is we draw a simple random sample of size n1 from an unknown population, from a normal population with an unknown mean, and then we draw another sample of size n2, and we calculate our confidence interval for mu1 minus mu2. That's going to be our sample mean of the first population minus the sample mean of our second population plus our critical t times our standard error. Remember that all of this right here, this is our standard error. So t star is our critical t of confidence level C for the t distribution that you can find from software, or you can find by taking the smaller sample size and then taking a look at table C, which I have posted on our Canvas course and is in the back of the book. So how do we conduct a hypothesis test for two-sample t procedures? So what we're testing is that mu1 equals mu2, and then our t is the difference in means over our standard error. And we find our p-values from the t distribution either using software or by taking our degrees of freedom, the smaller of the two, and then going into table C. So I'm going to end the video here, and the next video is going to have an example and a brief discussion of robustness.